So now let's proceed to the demos. The first demo is a distance relay tap testing demo. It is developed based on the Iec60255-OnetoOne Standard. The demo is developed in Hypersim, and there is also a test sequence programmed in TestView. In this demo, we're using the Iec60255 sample value and goose messaging to communicate with the relay under test. And we're using a model-based design and testing methodology just to create more realistic testing scenarios. Just a brief introduction on the standard. The Iec60255-OnetoOne Standard, it defines the functional requirement and the tap testing procedures for distance protection relay. So it makes it easier for us to compare the performance of distance relays from different manufacturers in terms of some critical criteria, such as the basic characteristic accuracy, average operate time, and overreach. The figure here, it shows a typical setup for a protective relay closed-loop testing. So the power system model will be simulated in Hypersim and running in real-time on a real-time simulator. The simulator will send out analog signals through a power amplifier to the device under test. For the trip signal to go back to the simulator, we could use either Iec60255 goose message or a simple digital signal. If the relay under test it features a low voltage interface, then we could directly connect from the simulator to the device under test. A third setup could be like what we do in this demo, using Iec60255 sample values instead of the analog signals. So here it lists the different functional tests defined in the standard. Basically, the tests include both the steady-state test and dynamic test. In all the dynamic tests, it is required in the standard that a power system model needs to be simulated just to generate more realistic test cases. And especially in the double in-fit test, it is mentioned in the standard that a real-time power system simulator can be used because we need to accurately simulate the behavior of the system after the operation of a remote circuit breaker or even after the operation of the relay under test. So the demo we are showing today is covered by the section 6.3 dynamic performance test. So here this figure, it shows the model defined for the dynamic performance test. It is a simple open-end transmission line model. It has two different configurations. It can be either a short line, which is 20 kilometers, or it can be a long line, which is 100 kilometers. The flowchart here, it shows the workflow to carry out the test. After you specify the length of the line, there are also other parameters that need to be varied during the test. So here we have source impedance ratio, fault location, fault type, and fault inception angle. And each of the tests need to be repeated for 4 times, just to obtain a more reliable and repeatable test result. So let's make a simple calculation. And there will be in total 1,792 tests to be done for one single line configuration. So just imagine how long it would take in the offline simulation software. The advantage of real-time simulation is if you carry out a 5-second simulation, it would take exactly at 5 seconds. So theoretically, we should spend like around 2.5 hours to finish the test. And from the test result we have obtained, plus the processing time, it took us 2 hours 48 minutes. So it is really a very efficient tool to carry out relay testing. This demo, it looks very much like a unit test for a single device, but the same testing methodology can be easily extended to test a more complex power system or to test a more complicated protection scheme. So here is the relay configuration tool for the MICOM P444 distance relay. And let's open the setting file for the short line dynamic performance test. And here we will be able to configure the CT-PT ratio, and then we will configure the protection scheme. So here we enable the distance protection scheme to cover the first 80% of the line. The next step will to configure the sample value ID so that the simulator and the relay can communicate with each other. Now we're going to open the IED configurator to configure the goose messaging part. So first we specify the IED name, and then we define some communication parameters. And now we create a dataset, and then select the data attributes we want to include in the dataset. The next step will be configuring the goose control block by specifying the MAC address, IP ID, and down here we just associate this control block with the predefined dataset. The last step will be exporting the SCL file so that later on we could use it on the simulator to configure the IOs. So now we're going to launch HyperSim. And then we will open the model for the short line dynamic performance test. So this is the same model as I showed you before. And on the top of the interface, you would see some menus that we use to edit the model and to start the simulation. And on the right panel, we have the libraries for different control blocks, and also we're working on the library for protection relay. And also we have a lot of power system components. We could drag and drop and build up a power system model like this. And here we have 3 fault breakers at the beginning of the line, at 50% of the line, and at the end of the line. So the relay should be able to pick up the first 2 faults, but not the last one, because it is outside the protection zone. So now we're going to establish a connection with the real-time simulator. And here we put the IP of the simulator. Then we do an analysis of the system, and it will generate a net list of all the components we have in the model. The next step will be applying the sensors. So now we open the sensor file. And in this case, we will be able to define the measurement and then monitor these measurements in scope view. And also we will be able to map the measurement to the I/O channels by using the sensor numbers. And in this demo, we're sending all the voltage and current measurement through sample values to the relay under test. Before we start the simulation, I just want to show you that in Wireshark, you can see that for now there's no sample value stream on the network. And then we could start a real-time simulation. After the simulation is started, and we could go back to Wireshark. And here you can see the sample value stream coming out from the simulator. And since we have the time synchronization option, so you see the sample sync is with the local clock. And here we could also use the Omicron SB scope to find the stream. and then we will be able to monitor the voltage and current measurement. So now we're going to open Scope View. And then we connect to the simulation that we're running right now. We open a template which is pre-configured like a template of the waveforms. And now we're going to acquire the steady state waveforms without any disturbance. And you can see the voltage, current, the trip signal, and then the status of the breaker. So we could easily change the acquisition time to 0.1, and there are many different ways to arrange the waveforms. We could put them in parallel or superimposed, and the waveforms can be shown in one column or several columns as you want. We will change back the acquisition length to 0.5 seconds. And now we're going to enable the first breaker, which is at the beginning of the line. And then we'll configure it to apply a double line to ground fault at 0.054 seconds. So back in Scope View, if we check Trigger here, then it will trigger the spot event at 0.05 seconds. As you see, we received the trip signal from the relay, and the breaker is open. And here we're using a cross time function just to determine when the trip signal change from 0 to 1. And in this case, we will be able to define the operate time of the relay. Now we're going to disable the first breaker, and then enable the fault at the end of the line. And this time we're going to apply a single line to ground fault. Back in Scope View, we'll acquire steady state waveforms first, and then we'll trigger the third breaker to apply the single line to ground fault. And here you see the faulted voltage and current. But the trip signal is always 0 because the relay didn't pick up this fault, since it is outside zone 1. Now we're going to stop the simulation and then launch test view. And here on the left panel, as you can see in this Iec60255 OnetoOne project, there are multiple studies, and they are developed according to the list of the different functional tests in the standard. And this is a demo test sequence I'm showing here, and it will be able to define which model you're going to use, and it could manually configure some component parameters. Then we have this snapshot function. It could save the steady state condition and then apply it later, so that all the tests they start from the same initial condition. And here we could read input parameters from Excel spreadsheet by defining the path and the range name. And during each test, the test view will save the waveforms, and it could also carry out some processing, such as using the cross time function to define the operate time of the protective relay under test. And then it could also save the test result into Excel report. Here we have the path of the Excel file, then the output range, and here we have the date when we carry out the test and the test result. And now I'm going to show you the Excel spreadsheet where we define the input and where we save the test result. So we have some introduction pages that just to introduce how you could use this Excel to define the test sequence. And also we explain what is the test model and some basic parameters of the model. In the input parameter page, we're able to define the test sequence. And as you can see, there are many different test cases being defined here. And the users just need to specify the source impedance ratio, fault location, fault type, and there will be a pre-configured template just to calculate the parameters for each component in the model. To do that, we need to specify the name of the block in the model. Like this is the fault breaker name, and then we have the parameters for this block, the switching time for each phase. So in this way we will be able to control which type of fault we are applying. On the output page, we have the starting and the ending date, and we have the operate time of the relay under test. And based on that, we could do some post-processing and calculate the minimum, maximum, and average operate time. We could also have a summary of the test result. And then based on these test results, we could have the SIR diagrams being plotted. So this gives you a better idea, a more visualized idea, how is the performance of the relay. We could also carry out some statistical analysis of the result. We could plot the histogram of the operate time. And in this demo, I just programmed 4 different test cases. They're all applied at the beginning of the line, but they're different fault type. And so the component parameters are being calculated using the template. And here is the output range. And I will delete the old result so that we will be able to see the updated result after running the test sequence. And here we are able to select whether we want to see the waveforms after each test, or we want to disable the scope view function. And now we start the test sequence. In the console, you will be able to see which parameters are loaded and which test we are currently executing. So now is the waveforms for the first test, a single line to ground fault, and we see the trip signal from the relay. we click OK, it will proceed to the next test. And this is a double line fault. And if we click Head, it will not show the waveforms after the test, and it will continue to finish the whole test sequence. Okay, so now the test is done. And if we go to the test folder, it's in short line demo H6. And in the data folder, we have all the COMTRADE file for each of the tests. And here is the PDF file of the waveforms. If we open the Excel report, then we could see the new test results are saved here. And we are able to see the operate time of the relay under different scenarios. If we go to Scope View, we could select the waveforms of the task that you are interested in and playback it. So now we're selecting the first task. And you see the waveforms here. And we could replace it by maybe the fourth one. And here you also see the waveforms.